In this lecture, we're going to learn about short-circuit evaluations. And this is one way we can save on the operations we are doing in a logical expression. What do I mean? If you are using the logical AND operation, if one of the operands is false, the result is going to be false because anything you're going to AND with false is going to become false. So we can take advantage of this and put operands that we think are likely to be false first. And when the compiler meets that expression that is likely to be false, it's going to know that the result is going to be false anyway, so it's not going to execute whatever is after that expression or variable that is false in the expression. The same logic applies to the OR operator. If you have one thing that is true and the entire expression is going to be true. So when the compiler finds one thing that is true in a potentially long operation, it's going to know that the result is going to be true anyway. So it's not going to execute whatever is after that variable or expression. I know this might be cryptic, so let's look at a few examples. Here we have a simple program. We have a few variables, A, B, C, D, and P, Q, R, M. And we're going to look at the AND operator. And we know that when we do the AND logical operation, if one of the operands is false or zero, the result is going to be zero. So if we have the expression like here, A and B and C and D, and one of them happens to be false, for example, B, the entire thing is going to be false anyway. But when the compiler hits B and sees that it is false, it's going to drop here and not execute anything after that. And this is referred to as short-circuiting. We have the same phenomenon for the OR operation. And if one of the operands is 1, the result is going to be 1 anyway. So if Q, for example, is true, we know that the result is going to be true anyway. So the compiler is going to stop at this Q. It's not going to do OR R or M because it knows it doesn't need to do that. The result is going to be the same anyway. So this is what we refer to as short-circuit evaluations. Okay, so this is why you should care about short-circuit evaluations, because they might save you from doing some potentially expensive computations in your logical expressions. Okay, so this is all cool, but how do we test that? How do we know that the compiler has actually stopped? Okay, here is an example that I tried and came up with. What I did is I wrapped all my test conditions in functions. So here we have a function called car, which is going to return a Boolean. We have a function called house, which is going to return a bool. We have a function called job, which is going to return a bool. We have another function called spouse, which is going to return a bool. And by return, I mean something we're going to get out of the function. We haven't really learned about functions now, but I really had to use them so that I can show that the compiler is actually doing that evaluation. And we're going to see that the compiler is going to stop and not execute other statements when it knows the result before it finishes the entire expression. So what we can do once we have this, we can do an expression like this. Suppose somebody is saying, I'm going to only be happy if I have a car and a house and a job and a spouse. And if one of those things is not available, I'm going to be sad. And one good thing about this program we have here is that we're going to see when the compiler actually goes in and try to know if this person has a house. And we can control that by what we return from this function. So if we return true, the person is going to be having a car. If we return false, the person is not going to be having a car, and they are going to be sad. And we're going to be able to see these things when we run this application. This is really all we want to do in this lecture, so let's head to Visual Studio Code and see this in action. Okay, here we are in our working folder. The current project is short-circuit evaluation. We're going to copy our template files here, and we're going to put them in our current project. We're going to go up one level and open this up in Visual Studio Code, and we're going to hop over in our main function and remove whatever we don't need. We are going to go down and put in some test code that we can play with, and this is a bunch of conditions, A, B, C, D, P, Q, R, M, and we want to show that with AND we can do short-circuiting if we find one operand that is a 0 before we hit the end of the entire expression. We can't really see this because these are a bunch of variables. We don't really have a way to see if the compiler is actually evaluating this, but we're going to run this and see the final result. So if we run this, D is false, so the result here is going to be false for AND, and we have a true value here, which is M, and the OR operation here is going to evaluate to true. So let's try and do this. We're going to bring up the terminal and we're going to build with GCC as we always do. The build is going to go through. We can clear and run Rooster, and we're going to see for AND result is false, for OR the result is true. So you can really try and plug in any values you have, but the fact is that if you have anything that is false in your AND logical operation, the compiler is going to evaluate this to false, even if that's an A. For example, if it knows A is false, it's not going to execute all these things. It's just going to give you the result because the compiler can see that this is going to be false anyway, because we have at least one value that is a false in our AND expression here. The same applies to the OR operation, but the special value is a 1, which is going to turn the entire expression to a 1 if we have a true or a 1 inside. So let's put together functions that are really going to allow us to see this. For that, we're going to comment this out because we don't want to have some noise output in our terminal. So let's comment this out. And we are going to go to the top in front of the main function and put in our functions. Let's close this by clicking on this Explorer icon here so that we can see the entire thing. We have 4 functions. One is called car. It's going to return a ball. And that really means that if we call this function, the call to the function is going to evaluate to a bool. And we can use that bool in an expression like we are about to do. We have another function called house that really does the same thing. And this setup is going to allow us to control what car, house, job, and house and spouse evaluate to. And we're going to be able to see these functions actually called. We're going to see this output and know that the compiler actually tried to know if this person has a job. Let's go down and put in our code. We're going to do that right here. Put in the code at line 51. And we are saying if car is true and house is true and job is true and spouse is true, I am going to be happy. If any of these things is not true, I am going to be sad. And we can go up and actually control if this person is happy or sad. So for example, we're going to give him a car by returning true here. We're going to give him a house by returning true here. Let's make him happy at first. We're going to give him a job by returning true here. And we're going to give him a spouse by returning true here. Now, if we look at this expression, we're going to call the car function. We're going to return true. And house, this is going to return true as well. And job, this is going to return true as well. And spouse, this is going to return true. So the entire thing is going to evaluate to true, and we are going to say that the person is happy. Let's try and build this with GCC. Bring this up and clear so that we don't have any noise in here. We're going to run Rooster, and you're going to see that the car function was executed, the house function was executed, the job function was executed, the spouse function was executed, and all these functions returned true, and we know that the person is actually happy because we can see the output here. One thing that is really important that we have in this setup, we can see these functions actually getting called. So what could happen if we didn't give this person a house? Let's take that house out and return a false here. So if we do this evaluation, car is going to return true, and this is going to be fine, and house is going to return false. By the time the compiler hits here, it's going to know that we have a false in here, and anything we can end with a false is going to be false anyway. So the compiler is going to stop here and actually jump here and tell you that the person is sad because he doesn't have a house. And the main message here is that we have short-circuited at this second operand here because it is false. And if we try to run this, we're going to see that the functions for job and spouse didn't actually get executed. So let's build this. We're going to build with GCC as we always do. After that, we're going to clear and we're going to run rooster. You're going to see that car function was called, house function was called, but by the time the house function returned, we know that the person is sad anyway, because it doesn't matter what you're going to give them because they don't have a house. And the only condition for them to be happy is for them to have all these things: a car, a house, a job, and a spouse. I really hope this makes sense. We can change the logic here, and we can change this to OR. Let's use logical OR, but I don't want to take this out. I want to leave this to you as a reference. So I am going to copy this and actually comment this out. Leave this here in code so that you can see this whenever you want. And I am going to paste that down here and change the operation to OR, logical OR. So we're going to change that to this. And now the person is going to be happy if they have one of those things. If you give them a car, they are going to be happy, even if they don't have a house, a job, or a spouse. The only way for this person to be unhappy is if they don't have either of these things. So if we go back to our function calls and not give them anything, so we're going to return false in all these functions, and we build and run. We're going to build with GCC. We bring this up so that we have some breathing room, and we clear and run rooster. We're going to see that the person is sad because they don't have a car, they don't have a house, they don't have a job, they don't have a spouse. So they are sad because that's what the expression we did here says. I'm going to be happy if I have a car or a house or a job or a spouse, but they don't have any of these things, so they are sad. But we can make them happy by, for example, giving them a house. Why not? Let's do a true here. And we're going to build again. We're going to do that with GCC, but before we run, we're going to try and look at the expression and guess what is happening here. So the compiler is going to go and, does this person have a car? We're going to get a false because they don't have a car. We didn't give them a car. Once the compiler hits house, it's going to notice that the person has a house. So it knows that now they are happy. So it can jump in here and say they are happy because anything we're going to evaluate on these things is not going to change the outcome. So job and spouse are not going to be executed in this case here. If we run this, let's clear rooster. We're going to see that car function has run. They don't have a car. So house function is going to run and we are going to return true. If you go up, you're going to see this. We are returning true in house. And the compiler is going to know that whatever we do afterwards is not going to change the outcome. So job and spouse functions here are not going to run. And we have saved on some potential computations we could do in these two functions. And this is really what short circuit evaluation is all about. So for example, if we are doing an OR operation like this, and we know that one of these functions is likely to be true, we're going to move it earlier in the expression and increase our chances of saving on useless computations that might be expensive and not do them. And this is going to improve performance in some cases, and I really wanted you to be aware of this. This is really all we set out to do in this lecture. I hope you found it interesting. We are going to stop here in this lecture. In the next one, we're going to see that we can use integral logical conditions. Go ahead and finish up here and meet me there.